Here's a look at how to solve numbers 20 and 21 on the Gravity and Uniform Circular Motion Review paper. Number 20, a satellite is placed in orbit 6 times 10 to the 5th meters above the surface of the planet Jupiter. Jupiter has a mass of 1.9 times 10 to the 27th kilograms and a radius of 7.14 times 10 to the 7th meters. We are going to find the orbital speed of the satellite. This picture is a whole lot like number 19, where we have the planet in the middle and the satellite going around the dashed line orbit here. In order to figure out what the actual orbital radius of the satellite is, we need to make sure that we take how far it is above the surface of the planet, the 6 times 10 to the 5th meters, and we add in the radius of Jupiter. Those two numbers have to get added together to find out how far the satellite is from the center of the planet. That's what I did over here. So I took the radius of Jupiter, which was given at 7.14 times 10 to the 7th meters, and I add the orbital radius given in the problem, which is 6 times 10 to the 5th. And I get 7.2 times 10 to the 7th meters. Now I know the force, just like with all these satellite problems, the force that's holding the satellite in orbit is the force of gravity. So the force of gravity is given by Newton's law of universal gravitation. The centripetal force, I'm going to use the mv squared over r version because we're looking for velocity. The thing that's orbiting is the mass that's in both sides, which is the mass of the satellite, so that will cancel. I have an r squared in the bottom here and just one r in the bottom, so this r cancels with the squared. And in order to solve for velocity, I just have to take the square root to get rid of my squared, which is why on the left I have the square root of big G, mass of Jupiter, divided by the orbital radius. Plugging in the numbers, I get the big G, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, which is the same everywhere in the universe, times the mass of Jupiter, which was given in the problem at 1.9 times 10 to the 27th kilograms, divided by the orbital radius, which we solved for, of 7.2 times 10 to the 7th meters. Once I plug that into my calculator, I find out that the satellite has an orbital speed of 41,954 meters per second, which is very, very fast. Moving on to number 21, Newton's cannon, which is a hypothetical cannon that could fire a bullet from a mountaintop so fast that it would fall toward the Earth at the exact same rate that the Earth falls away from the bullet. Thus, the bullet would never fly off into space, but also never hit the ground. Basically, it was a hypothetical cannon talking about putting a satellite in orbit. We're going to calculate the velocity that a satellite shot from Newton's cannon must have in order to orbit the Earth 150 kilometers or 150,000 meters above the surface of the planet. And we also want to find out how long would it take to come back to the cannon again? How long would it take to go around once? So the radius above the surface of the planet is the 150,000 meters, but we also have to have the radius of the planet to put the two together to find our total orbital radius, and that's 6.371 times 10 to the 6th meters for the radius of the Earth. Mass of the Earth, we know that, is 5.972 times 10 to the 24th kilograms. We're trying to find velocity. We're trying to find time. First, I got to figure out what is my total orbital radius. So I'm going to add the r's together, the radius of the Earth, and how far it is above the surface of the planet. So I put in the Earth's radius, 6.371 times 10 to the 6 meters, and I add that 150,000 meters to get a total orbital radius of 6.521 times 10 to the 6 meters. Now I know that the force of gravity is equal to the centripetal force, because gravity is what holds all satellites in their orbits. So for gravity, I'm going to use Newton's law of universal gravitation. For centripetal force, I'm going to use mv squared over r. The mass of the satellite cancels because it's on both sides, just like in the previous problem, and r squared in the bottom cancels with the r on the right, leaving me with just one r on the bottom left side. Taking the square root to get rid of my squared gives me the square root of g, mass of the Earth, over the total orbital radius. Plugging in my numbers, I get 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared for big G. Mass of the Earth, 5.972 times 10 to the 24th kilograms, all over the total orbital radius, which I solved for at the beginning of the problem, 6.521 times 10 to the 6th meters. Plug that into my calculator, and I get a speed of 7,816 meters per second. Now I know that you have an equation on your equation sheet that solves for the time a satellite takes to go around once. You could use that if you'd like. I just used the speed equation How fast does a satellite go? Well, it's how far it goes, the circumference of the orbit, divided by the time. And I just did a little algebra, multiplied the time over, and divided the velocity down into the denominator to get time equals the circumference divided by the speed. Circumference is 2 pi times the radius that we solved for at the beginning of the problem, divided by the speed that we just solved for, 7,816 meters per second. And I know that it would take that satellite 5,242 seconds to go around the Earth, but since you're probably not familiar with measuring things in thousands of seconds, it would take just shy of an hour and a half, or 87.4 minutes.